Hey everyone, welcome back to another 7-minute math video. The last piece of factoring we're going to work on this week is going to be factoring special cases. Now, before we deal with factoring special cases, I guess it's important in understanding what in the world a special case is. I've got all these different expressions here, and some of them are special cases. Well, that one's upside down. Some of these things are special cases, and some of them aren't. And if you know which ones are special cases, then you can apply a special rule to those special cases, and it makes your life a whole lot faster. The problem is, how in the world are you supposed to know which ones are which? If you can identify which one is which, then you're in great shape. But if you can't, then you're left stuck kind of factoring like normal. So that brings us to the question of, should we memorize a rule just for the sake of memorizing a new rule? So let's go ahead and talk about what a special case looks like. All right, here we have a special case. Now, this is a special case, and I'll show you why. First, it's a trinomial. The thing that you'll notice about this one is that if I took the 16 and I square rooted 16, and I'd get 4, and I took the 1 that's in front of the x and I square rooted the 1 and I got 1, and I took 1 times 4 and I got 4, and then I took that product and I doubled it, I'd get 8, which is exactly the same as this. That's what makes this thing a special case. You're going to have to remember that if you want to use the rules for special cases. Here is the third and final special case that I'm going to show you as an example. This one's different because it's not a trinomial, but what I do observe is, well, a couple things. First, I notice that this and this are perfect squares. I notice that this is the square root of 81, which is 9 squared, and I notice that this is 16, which is 4 squared. So I recognize that these are these squares, and I recognize that this is even. That's key. And I recognize that it is a subtraction problem, the difference. This is technically called the difference of two squares. If you see that, fantastic. But if you don't, you might find yourself wondering, well, what's the point of memorizing all these new rules if I may or may not remember what they are? Let's spend our time talking about how to factor something, whether it's a special case or not. Then you don't have to worry about memorizing a bunch of new rules. So I have a trinomial. It may or may not be a special case. It appears like it might be, but again, I'm not going to really focus on the memorization piece. My first term goes here. My last term goes there. There's a lot of other videos that I can link to if you need to see how this all works. Y squared is y times y, and the 64 has lots of different combinations that multiply together. 4 times 16, 5, 6, 7, 8 times 8, that multiply together to give you 64. And I need a pair that adds or subtracts to get 16. And the only pair that works that adds or subtracts to get 16 is the 8. Now, a couple things I need to note. If this is 8 and this is 8, and I need the two 8s to go together to become negative, both 8s have to be negative. And that makes negative 8y and negative 8y. Notice that they're the same. The fact that they're the same means it's a special case. But again, how do we finish this problem out? Now that we've checked it, y squared, negative 16y, and positive 64 is the same as what we started with. So now I'm going to write y minus 8 from the left-hand side, and from the top, y minus 8 from the top. And because these are the same, we're going to write this as y minus 8 quantity squared. So this equals this. Second example. Once again, I have a trinomial that I'm going to factor. I'm looking now because I want to be a little more aware. There's no GCFs here. So with no GCFs, I'm going to set up my area model, my 9y squared, my plus 4, and I'm going to immediately start thinking about combinations that multiply to give you 9y squared, and combinations that will multiply to give you 4. And what I want to find is a combination on the left and on the right that will produce 12. And 3 times 2 is 6, 3 times 2 is 6, and 6 and 6 make 12. So this is going to be the combination I'm going to go with. So 3 and 3 with the y go here and here. 2 and 2 go here and here. And everything's positive. So I'm going to do positive, positive. And here we go. From the left-hand side, 3y plus 2. And from the top, 3y plus 2. So therefore, 3y plus 2 quantity squared is the answer to this question, is the factored form of this question. Not all polynomials have 3 terms. Sometimes there's only 2. If there's only 2, you can do a couple things. First, you may want to consider memorizing this rule. This is, as we mentioned a couple pieces of paper ago, on this one, this is going to be the difference of two squares. This is one of the few that I actually memorized when I was your age and learning this for the first time. I knew my perfect squares. Those are numbers multiplied by themselves. And I knew that difference was subtract. So when I observed that happening, I could immediately identify that there was a special case. So I'm going to show you what to do if that happens. But let's say you're really not good at memorizing. You could go ahead and just expand this binomial into a trinomial like this, right? I'm going to go ahead and basically use this middle term 0p as a placeholder so that now I have 3 pieces and I can start working on my area model. But here comes the shortcut. This is one I like. The difference of two squares, right? 1p squared is just p times p, and 36 is 6 times 6. So I'm going to write p and p. That takes care of this piece. 36 is 6 and 6. And because I want them to be opposite, because I need a negative 36 produced, one of them's plus and one of them's minus. And this is the answer. Now, I really do think that one's worth memorizing. And just to make sure that you don't get surprised by this, let's take a look at one more. This one right here looks like the difference of maybe some squares, but 18 and 128 aren't anything that looks familiar to me. Well, one thing I do notice, though, is that they're both even, so maybe I should mess around with taking some stuff out. If I took out a 2 as a greatest common factor, I'd get 9h squared minus 2 goes into 128 64 times, and no, nothing there. Oh, look at this. So 9 and 64 are both perfect squares. So watch this. I'm going to go ahead and imagine what times what equals 9h, and that's 3h and 3h. And what times what equals 84? 8 times 8. And they have to be opposite signs. So one's plus and one's minus, and we're done. So this is, in fact, a much faster way. So while I don't really love the trinomial piece, I really do like the difference of two squares.